Hey Android and KTOR devs. If you've read my title, then you might be wondering, what the heck has Sarah gotten herself into this time? Well, for some overly ambitious reason, I decided that I wanted to try out some machine learning. And man, guys, I really had no idea what I was getting into. Machine learning isn't just about coding. It's a whole new world of unique concepts, terminology, math, and science. So, as a Kotlin developer, why did I put myself through all of this extra learning? Because I really do believe that businesses will come to rely on machine learning more and more to maximize their in app functionality, features, and purchases. From object identification to recommending similar items on product detail pages, machine learning models can greatly enhance a company's profit. And not only that, but well trained models can really enrich our apps with great user experiences. I was curious to see what the industry demand was. To find out, a quick search on Indeed showed me 386 remote jobs for TensorFlow. And PyTorch was a close runner-up with 276 jobs. Could be wrong, but I suspect these numbers will grow in the next few years. Which led me to my first decision. Should I use TensorFlow or PyTorch? There's a lot of debate on both. After doing some research, I was really tempted to start out with PyTorch. It's quickly gaining a lot of popularity. But at the end of the day, I found more examples for TensorFlow. And since I wanted to deploy an Android on-device model, I decided that going the Google route would be the best for my Android implementation. With that decision made, it was time to start learning and coding. I'm familiar with Python, and I was a Microsoft SQL Server admin for over 10 years. I have a really good background working with CSV files and manipulating data, so I wasn't coming into this as a total beginner. To get started, here are a few tips that I learned along the way. Before you check out the code examples, first, make sure to learn the concepts and terminology. Things are so different in this world that the examples might not make much sense until you learn what the heck things like ReLU and dense layers are. Next, make sure that you're comfortable with Python. As a developer, this is really win-win because Python is great to have in your development stack, even if you decide to not become a machine learning expert. Nope, at this point, you're still not ready to code a model just yet. Next, make sure that you're familiar with the NumPy package, especially working with arrays and data types, and the pandas library, especially working with data frames, data frame queries, and data frame manipulation. Okay, now finally, you're ready to start looking at some examples. That is, unless you're like me and wanted to take things one step further. I still have my research cut out for me, and next, I learned all about recommendation systems. If you've been following along, you know that I've been working on a food tracker app that uses the Open Food Facts database. Implementing some sort of machine learning model was always my main goal with this project from the start. There's so much data to work with and so many possibilities. My mind was racing with ideas. To stay in fighting shape, I follow a keto lifestyle. My first thought was that users could like their favorite products. All of their likes could be saved to a Room or a Firestore database. Then, my app provides recommended products based on the fat and carb values of all of the products that they like. The best place for me to start was the TensorFlow Movies Retrieval tutorial. This guide uses user movie pairs to recommend movies that a user might like. With my plan in place, next I needed some food and barcode data. Open Food Facts provides an advanced search feature that allows you to download a CSV snapshot of the results. I ended up with about 3,000 records of great value products, which provided a pretty good set of fat and carb options. Here's an overview of the tab-delimited CSV file with barcode, product name, and the nutrition information for each product. It was just what I needed. Now, the dilemma. What about my user data? The Movie Lens dataset provides pre-populated user data in the TensorFlow tutorial, including a user ID, a movie ID, and also a user rating, which rates the movie from 1 to 5. But for my app, I didn't have any user data, and users' favorite products aren't ranked, they're just likes. Not having enough pre-existing data is known as a cold start, and I did my best to work around it. First, I created some CSV files with pre-populated user favorites. This was pretty time-consuming because I had to go through and handpick certain items to match certain diet types. I gave up on this method pretty quick. which turned out okay because once I got comfortable with working with data inside my models, I was able to create data sets for each diet type based on a custom field that I added to my product data set called food diet type. So here you can see I have a keto user and then a high carb user, and I did this for each diet type that I wanted to add. I'll create this food diet type column by creating a conditional dictionary, then using NumPy select. So here's my condition. And like for high carb, I say carb value has to be greater than or equal to 30. And I just go through the different types of diet types and call np.select conditions.values. After a few attempts at completing the entire model, it worked, sort of. I was able to train and use the model successfully, but then I started wondering how well it would perform in my app. For one thing, the custom user tables that I created from the primary dataset weren't really realistic. Second, the user likes functionality doesn't exist in my Android app just yet. And third, woohoo! After all of that learning, I finally got a model working. I wanted to experiment and see what else I could do. After building lots of practice models and trying all sorts of different things, I wound up with 30 collabs in Google Drive. And the further I strayed away from the TensorFlow tutorial, the harder things got. There are so many different ways to load data, create models, and create layers. And until you understand things like using the sequential API versus the functional API, it can be really difficult to port examples into your own implementations. In the end, I decided to go with an item-to-item recommendation system instead of a user-item pair. It was much easier to integrate this into my app. And even though I have a bunch of fancy ideas for the future, for this round, I also ended up following the TensorFlow tutorials pretty closely without too much customization. Next, I'll step through my final model and show you what it looks like. This is usually the Android part of my videos, but today I'm here in Colab with my final model. I've gone ahead and run everything already, so we don't have to wait for the scripts to execute. This way, I can just go through each block step by step. First, I install everything that I need for this model. Most importantly, I'll be using the TensorFlow Recommenders API to subclass my combined model and run the retrieval task. So here I go ahead and install everything for my environment. Then I add all of my imports. And I check my TensorFlow version here. Next, I uploaded my Open Food Facts CSV file to Google Drive so I could easily access it from Colab. In this block, I connect to Drive and create a symbolic link so I can access it as /my_drive without the space. So here we go ahead and mount it, and here's the symbolic link to my drive. Let's go ahead and take a look at this file before we start the pre-processing steps. So here I am in my Google Drive, and we've got the barcode, the product name, the fat value, and the carbohydrates value. This is a handy function to clean my CSV file. As we saw, some of the fat and carb values are floats, so I round them to solid integers. I also drop any null data. So this is my pre-process function. It takes a pandas data frame, and inside I just check for nulls, and then here's where I round the fat value and convert it to an int. Now, I upload my data with pandas. One small tricky thing here, and yet very important, is that the code column imports as an integer by default. This is a huge problem because this drops the 2 zeros in front of some of the barcodes. That means when I pass in a barcode from my Android app, they won't match, and the data types will be different. I easily got around this by specifying the D type of string for the code column. So here we call pandas read CSV. Then I'm accessing my drive here, and the CSV file is called food final, and I set the data type of the code field to string. Now, if we look here back in Drive, you can see even Drive thinks that it's an integer, and it drops those 2 zeros. So when you're pre-processing data, make sure to check for things like that because they can really impact your final results. Once the CSV file is read, I call the pre-process function and pass in the data frame. Next, it's time to create my custom food diet type column. This block is slightly different than the example from my earlier slide. After learning more about feature preprocessing and text embeddings, I decided to make the diet type column a numeric categorical range from 1 to 5. So here I create my conditions, and this takes in the data frame conditions. So I check the carbs value, And if it's greater than or equal to 30, then it's a high carb diet type. Then I just go through the different diet types, and then I call MP select and use the conditions and set the default type to 5, which is standard. Here's how the final pre-processed data looks. I have a length of about 3,300, and here I have the code, and as you can see, we have the 2 padded zeros here, the product name, and look, the fat and the carbs have all been cleaned up to integer values. And then I have the custom column here, which is the food diet type, and we've got a wide range of diet types here, so this is looking good. Next, I create my training, validation, and test data frames from my food data import. There are so many ways to do this. MP split was really easy and works okay for this model. This method allocates about 80% of the data to the training data set and about 10% to the validation and test data sets. I think I need to revisit this later. I definitely need to add more data to my validation and test data sets, but for now, this works fine. So if we look down here, this gives us about 2,600 training examples and about 330 validation and test examples. To fit my model, these data frames then need to be converted to tensor datasets. To do this, you call from tensor slices and then pass in the pandas data frame. Here, I get a list of only the barcodes, just like the movie titles from the TensorFlow tutorial. Now, I'll prepare for my embedding layers by getting all of my unique features, which in my case is barcodes as string, fat value as int, carbohydrates value as int, and food diet types as int. So here, for unique barcodes, I batch the barcodes dataset into batches of 500, and then for the unique user fat, it's just a range of 1 to 200, and that's the same for carbs. And then unique diet types is a range of 1 to 6, which is actually 1 to 5. And then if we print this out, we can see we've got the unique barcodes here, and then we've got the fat values here, and then finally we have the food diet type, which is 1 to 5. At this point, I'm ready to build my models. The TensorFlow Movie Lens tutorial just creates a simple user model. So here they create a user model variable, and they create a sequential layer with a string lookup. But since I needed to add several embedding layers, here I inherit from tf.keras.model. This item model includes all of the item features that I want my model to consider during the retrieval process. In this model, I use unique feature arrays to create my sequential embedding layers. Barcode is a string lookup, and the rest are integer lookups. Here in the item model, I call a string lookup for the unique barcodes. Just to note, order is really important here. When I had diet type below fat and carbs, it really made a difference. I still need to learn about weights and how I can build better relationships between my features. But I just wanted to mention that in case you're playing around and trying different things. So here's the diet type embedding layer, and that's an integer lookup. And then we have the fat and we have the carbs. Next, I expand on my item model to create a deeper retrieval model. This query model adds the embedding layers by calling self.embeddingModel equals item model. Then it adds the dense layers and sets their activation to ReLU. This can help capture complex relationships between my features, mostly fat and carbs. Layer sizes is a parameter, so I can experiment with deeper model sizes. For example, I could start out with 32, then try 64 and 32, and then try 128, 64, and 32. So far, though, my initial tests show that creating a deeper model doesn't come back with great results. This might be because my dataset is too small and I'm overfitting. But for now, I'm leaving it in here in case I want to expand and continue to experiment. So in this model, you can see the item model is initialized, the dense layer is created, it loops through and sets the activation, and then finally for the last layer, we do not set an activation type, and we just add the dense layer with the layer size. This next block creates the embedding layer for the candidate model, which in my case is the list of barcodes from my CSV. Embedding layers convert raw values to usable, trainable formats. Here, I add a barcode vectorizer. This step is really important so that I'm able to pass a raw string from my Android app. Otherwise, if the text vectorization did not occur inside the model, I believe that I'd have to export all of the integer barcode mappings to a JSON file. Then I'd have to include that JSON file in my app, or maybe serve it up from an API, and look up the corresponding barcode to integer values. This is one of those lessons that I had to learn the hard way when I was using my food diet type as a string in one of my earlier models. Here I set the max tokens to 10,000, and I have a string lookup for the unique barcodes. Here I set up the vectorizer, then I create the text embedding, and by calling adapt on the unique list of barcodes here inside the model, I believe this is the final step that allows me to pass a regular string array from Android. Similar to the query model, this model just combines the embedding layers with the deeper dense layers. So in this model, we're initializing the barcode model, and then creating the dense layers and looping through and setting the activation. Now, it's time to combine everything together into one final model. This model sets up the query model, the candidate model, and defines the retrieval task. Let's say we pass a barcode of 888. When using factorized top K metrics, the model will check to see how often that same barcode is returned in the retrieval query. This helps determine the model's categorical accuracy. So here in the combined model, which is called recommended model, we set up the query model, the candidate model, and then set up the retrieval task. This is the loss function that defines the embeddings, then returns the retrieval task. So we've got the query model inputs, and we've got the candidate model inputs, and then it returns the task. Caching the training dataset improves performance, allowing the second iteration over the dataset to be much faster than the first one. If you cache your training dataset, make sure you also cache your test and validation datasets, or you might have issues when you go to fit your model. So here we create a cache train, a cache test, and a cache validation. With everything set up, it's time to create and use the combined model. Here, I go ahead and instantiate a shallow model, then I compile it. So here I create the recommended model with a size of 32 and compile it. Next, I fit the model with my cache datasets. So you just call model fit. And here's the cache train, and I'm using 50 epochs with my cache validation dataset. When it's done, it will print out my top K accuracy scores. I don't think that I'm getting good evaluation numbers yet. I think that's because I'm not working with enough data. This is something that I need to revisit in the future. So here I call evaluate on my cache train and my cache test, and then I print out the final accuracy scores. When the training results print out, let's scroll over and take a look at the total loss. So let's see, regularization total loss, here we go. So as you can see, the number starts out at a really high value, and as we iterate through each epoch, this number gets lower and lower and lower and lower. So we go all the way down, and it finally ends at 0.4892. And now down here, I have the printout of my total training accuracy and my total test accuracy. These numbers don't seem quite right, so again, that's just something that I have to revisit in the future. This next block creates a brute force index layer, which inherits from top K. I'll pass my query model to the constructor, which allows the index to accept raw feature values. This means that I can pass in data to the index without worrying about string or integer lookup conversions. Brute force index layer returns a tuple of top candidate scores and top candidate identifiers. For example, a float value of 17.67, which is the top K score, and the recommended barcode as a string. I pass in the barcodes dataset to build the retrieval index. Something that's very important, which again is something that I learned the hard way, is that this index is what you actually save when you save the model. So basically, this last brute force index layer becomes your final model. So here I create the index as brute force, pass in the query model, and then pass in the barcodes dataset. With the index created, you can now use it to pass in your own query independent of the training dataset. Here, I pass in a keto barcode with a fat value of 15 and a carb value of 2. Earlier, I mentioned that the brute force index returns a tuple of scores and barcodes. Here's where we can see what this looks like, and this is really important because I'll need to handle this output from my Android app. When I call the index, I can create my scores and barcode variables. Here, I just print out the scores. Notice how they are listed in descending order based on what the model thinks is a good match. Then, I can iterate through the barcode recommendations and map the recommended barcodes to my training dataset so I can see what type of products my model is recommending. So here, I create the two variables, and I call the index, and I'm passing in a barcode, a fat value, a carb value, and the food diet type. And then I make sure to print the scores. and I get the results as a list. And then I iterate over that list and I map the barcode to my training data set. So if the code matches what's in the training data set, it's going to give me all of my values back from the original table. And here you can see the scores. So here they are in descending order. Now let's take a look at what kind of products it brought back. And I can tell you it's not perfect. So we've got our product name, we've got some turkey breast, some wing sauce, and some creamy Caesar dressing. They all sound like keto values. But if we look over here, your diet types vary. So we have 2, which is keto, and then we have a 4 here, and a 2, and a 2. So it's mostly keto values, but again, it's not perfect. And this is just something that I need to learn. I need to figure out how to really let my training model know that I want fat and carbs to be the most important thing when it's training this data set. I've run a few tests, and overall, I'm pretty happy with the way the results come back, so I just decided to keep on moving forward. All of those embedding layers, dense layers, and separate models can get pretty confusing. It would be great if we could call model.summary to see what everything looks like, but I wasn't able to get that to work with this structure, even when I tried to call it after model.fit. What I can do is call index.summary though. This gives us a little bit of information on the query model. The parameters are all of my learnable features that the layer will weigh and evaluate during training. So if I call index summary, I can get the model as a brute force, and then I can get my parameters here and the total parameters here. Plot model is another way to visualize a model, but unfortunately for an index, I only get an image that says brute force with no other information. So here, if you call keras.utils.plotModel, it prints out this little image here. That's pretty much it for creating the model. Now it's time to save it. First, I simply call index.save. If you try to do something like model.save and then pass the path, you'll get an error. With this structure, I can only save the index. Instead of a temp or nested directory, I like to use a /models path, so the output file saves right to my Colab root directory. It's much easier to find it this way, and I'll show you how that looks now. So you just click on folders, and then here you get a models path right here. And I'm saving it under product recs, and then here's my model information. So here's the save model.pb. So you just call index.savePath, and you're good to go. Next, I load up the save index and I try it out. This time I'll pass in a high carb diet and see what it comes back with. So you actually load up the save model that was saved with index.save. Then I just call the same thing. I have my barcode recommendations, and this time I'm passing in a fat value of 3 and a carb value of 74. So let's see what's brought back for us. Pancake and waffle mix, that sounds high carb. So let's check out the diet type here at the end. So we've got 1, 1, 1, 1. That's great. It looks like it's mostly 1. So this time it did pretty good. And again, like I said, I did some testing here and there, and overall it seems to bring back really good results. Index.save saves the model as a TensorFlow save model, which we won't be able to use in Android yet. Next, we need to convert that save model to a TensorFlow Lite model. Here, I faced another issue the first time around. I found that I needed to add the TensorFlow op support. Here's the error that I got when I tried to convert it. So you get this hash table v2 error, and it says that the op is neither a custom op nor a flex op. This is because of my integer lookups. Behind the scenes, the integer lookup embedding layers create a map table, which isn't included in the TensorFlow Lite built-in operator library. Luckily, there's a workaround. I just needed to add the right converter options, and then I was good to go. You'll need to add additional Android dependencies because of this issue too. I'll go over that once I'm finished with these last few steps in my Colab. For more information, you can check out this link here. This block converts the save model, so you call tf.lite tf-lite converter from save model, and then you pass in the path. And then here's the ops support, so you just pass in tf-lite built-ins and select tf ops. And then finally, you call converter convert, and then you create the tf-lite file. So if we go over here, here it is. We've successfully converted the save model to a tf-lite file. Now that the hard part is done, it's time for some even harder stuff. I'm just kidding, sort of. This part's kind of fun. Once you download your TensorFlow Lite file, there's this awesome app called Netron that lets you visualize your model. Once it's loaded up, you can see your inputs, your input data types, the input order, which is awesome, outputs, your output data types, and then the output order. This information is a must to know when we're ready to start sending and receiving inputs and outputs from our Android app. You can also see the hash tables that are created for the integer lookups and the brute force top K layer and all sorts of cool stuff. To the developers of Netron, I just wanted to say awesome job and many thanks for this amazing tool. Here's the link for more information, so you can find it on GitHub here. Here's what the app looks like, and I've loaded up my TF Lite file. So here we can completely visualize the entire network. At the top, we can see the hash tables and the lookups for all of the embedding layers. So we've got carbs, the barcode, the fat, and the food diet type. And if I just click here, then I can see all of my inputs. So I've got food diet type is an N64 at location 0, and then fat value is an N64 at location 1, and again, the rest of the features here. And then down here, I can see my outputs. I can see that first I get that score that comes back, which is a float 32. And then finally, I get the barcode back as a string. In addition to Netron, we can also get an idea of how Android will handle inputs and outputs by using the TensorFlow Lite interpreter. Here, I read my TF Lite file, then get the details about my inputs and outputs. Next, I use interpreter.setTensor to set my input values. This is similar to how I use the index to get recommendations, but for the interpreter, I'm not using names. Instead, I use the input index and set my inputs in the order that they appear in the Netron preview. For the outputs, it's just like the index. The interpreter will bring back the scores and the barcode recommendations. My Android app also uses the TensorFlow Lite interpreter, so this is a really good preview of how things are going to work inside the app. In this block, I load the TF Lite model and allocate the tensors. Then I get the input and output tensors, and I'm printing out some information here. And now here's where I'm actually setting in the features. I set the inputs in order from 0 to 3, and this is very similar to what things are going to look like inside the Android app. For input detail 0, I've got the food diet type. For 1, I've got the fat. For 2, I've got the carbs. And then finally, I send the barcode in as a string. To get the scores, you call interpreter.getTensor, and for this we want the output detail 0 because that's going to be the first part that comes back. And then finally, to get the barcodes, you call output details 1. Here's a printout of the input details, and we can see similar information that we saw in Netron. And then here I print out the scores. Again, we can see them come in descending order. And then finally, the recommendations here. So now we know that everything's looking good with the TF Lite interpreter. We can be confident that once we add it to our app, things should also work good there. Another handy tool is the TensorFlow Lite Analyzer. This by far gives us the most detail from Python. Here we can see the input shapes for the embedding layers and dive a little deeper into the structure. Here's the printout of the analyzer. And again, you can see the hash tables printed here. If we go down here, we can see even more information. We can start seeing some of the inputs, the food diet type, the carbohydrates, and we can see data types here. And at the end, it gives you some information about your model size. And finally, I've won the first half of the fight and my model coding is done. Now it's time to import the model into Firebase. You can do this automatically if you'd like to, which would be awesome for an automated CI/CD pipeline. There are quite a few steps involved though, so for me, it was just easier to download the TF Lite file. If you'd like to learn more about the Firebase ML SDK, you can check out this link here. Once your TF Lite file is downloaded, you'll need to create a Firebase project. Getting the right link is a little hard to find in the console. From your open project, just use /ml/APIs and you should be good to go. In the callout, it mentions MLKit. If you click Learn More, it takes you to the MLKit homepage. The MLKit offers pre-trained on-device models that integrate right into your Android app. For certain models, including the recommendation model, you can use the pre-trained model or customize the model with the TensorFlow Lite Model Maker. I didn't go this route. I really wanted to do everything from scratch so I could learn the fundamentals. TensorFlow provides samples and custom scripts, but at first glance, honestly, this seemed a bit overwhelming to me. I just didn't know enough to dig in and make my own customizations when I first started. Plus, I was curious about what was going on behind the scripted examples. I'm glad I did everything from scratch. I learned so much creating my own model from the ground up. But now that I sort of know what I'm doing, it would probably be a good idea to give all of this a second look. I imagine things have been optimized much better than I could do on my own, and it seems like using the ML kit is best practice for new Android apps. Okay, back to Firebase. Since I didn't use ML kit, I can click on Custom from the Machine Learning console. Here, I can add, replace, download, and delete my custom models. Next, I'll go over my Android setup. First, I add Firebase to my project. For this, I needed the Google Services.json file, the Google Play Services plugin, and the Firebase BOM. Without using MLKit, it was a little hard to find the right TensorFlow Lite dependencies to add, but the following worked for me. I used Firebase ML Model Downloader KTX to download my custom model. Then, I added the TensorFlow Lite and TensorFlow Lite support. And finally, I added TensorFlow Lite Select TF-ops for the hash table integer lookups. For the ops support dependency, I also needed to add the Sonatype repo. At this point, I must admit, it was really nice to be back in Kotlin land, but my work was still cut out for me. Next, I created a recommendation service. Just a quick note, the code that I'm about to show you in the next few slides might be a little outdated and different from using MLKit. It was still a useful experiment for me though, so I'll just buzz through everything pretty quick so you can see how it works. This service takes in my food repository so I can process the barcode recommendations and also a coroutine dispatcher so I don't have to hard code dispatchers.io. Next, I define a variable for the TensorFlow interpreter, just like we use the interpreter in the Colab. I also set up an empty list that will hold my recommendations that come back from the OpenFoodFacts API. Here's what that data class looks like, which I'll use to populate the front end. My download model function is suspending, so it can run in the background while my app fetches and sets my custom model. First, I set up some basic conditions. Then, I get the instance of the Firebase model downloader. Next, I simply call getModel. Here, I pass in the model name, which is what I specified in Firebase when I uploaded the model. Latest model checks for the latest model and downloads a new model if needed. If not, it will just use the local copy. If getModel is successful, I set the interpreter from the task custom model result. You'll get some really useful messages in Longcat when the Firebase model download does its thing. So here you can see we need to download a new model, schedule a new downloading task, and then the model was downloaded successfully, and then it moves it from external storage to the destination folder, which is inside of my app. Very cool. And then finally, the model file is set. Now, it's time to put all of that Netron awesomeness to work. I know my input data types and the order that I need to send them in, so let's start building out some arrays. Here, I set up my arrays in the same shapes that my model expects. So I have each of my features as an array, and then I combine all of those features into one input array in order. So here you can see I have the diet type, and I have a long array, and then I have a function that actually takes the fat and the carbs and returns the long that matches the diet type, which is going to be 1 through 5. And then I have the fat value as a long array, the carbs, and then finally the barcode is a string array. So then I take all of these arrays and put them into one single array with all of the features. I had to format my outputs a bit differently. Here I set up a one-row array that holds an array of floats for the scores. I do an array of nulls for the barcodes, which is basically just a placeholder for the barcodes that come back from the model. Then I create a hash map where the first index stores the score array and the second stores the barcode array. So here we have a place for the scores that come back, which is one row of floats. And then we have the barcodes, which is one row of null strings. And then finally, I have the hash map, which you need to use for the interpreter. And inside the hash map, I create two indexes with the score and the barcodes. Now finally, in this beautiful, life-altering block of code, all of my hard work is paid off and I've won the battle. I call run for multiple inputs outputs on the interpreter, which fills my arrays with the model's response. Next, if the recommended barcodes come back with the barcode that I sent, I filter that one out and then take the top 5. And finally, I pass those 5 barcodes into my repo and get the recommended results. The rest of the implementation is just basic view model compose stuff. So next, here's a quick demo of how it looks in my food tracker app. Now that I've successfully integrated an on-device machine learning model from start to finish, I feel like I have a fighting chance to prepare for another match. The question is, should I? What do you guys think? Let me know if you'd like to see me integrate this same exact code with MLKit and PyTorch. I'm really looking forward to reading your comments and to see what you guys think. And that's it for today. Thanks for watching.